Good morning. Welcome to NGSS Physics. So today we're going to be talking about the dynamics of Newton's laws. And the dynamics of Newton's laws, the heart of it was forces. So that's what the topic is today. This is 1b.3. Here's Isaac Newton. One of my favorite quotes is when Isaac Newton said, "If I have seen further than others, it's by standing upon the shoulder of giants." So today we're going to try to stand on Newton's shoulders and see what we can see. Okay, kinematics that we just went over was the study of motion itself. Dynamics is the study of what causes that motion. Here we go, Newton's first law of motion. Some of you guys probably know this as inertia. The first law of motion, or the law of inertia, simply states that if an object is resting, it stays that way. Or if an object is actually in motion, it stays in the exact same motion, unless it's acted upon by an external force. Newton's second law. This is the force formula. Force is equal to mass times acceleration. So if a force, an overall force, is exerted on an object, it will change that object's motion. And it describes the relationship between mass, that's what m is, and acceleration. That little squiggly that you see right there, that just means the sum. So if all of the forces acting completely cancel each other out, there is no change in the motion. But if you add up all the sums and they don't cancel out, then there may be a change in the motion of an object. All right, let's take a look at the units for force. Now that we've got that formula, the units for force are derived from the units of mass and acceleration. We measure mass in kilograms in physics. We measure acceleration in meters per second squared. So the units are kilograms meters per second squared. We shorten that up and just call those units all together a Newton, after, you guessed it, Isaac Newton. All right, let's do a little practice with our force is equal to mass acceleration problem number 1. A 20 Newton force is pushing a 10 kilogram object to the right. If there are no opposing forces, what is the acceleration? Remember, an acceleration is a change in the velocity. So this is going to be a change in the motion. There's the formula. Manipulate it so that you're solving for acceleration. Plug those numbers in. You should get 2 meters per second squared. Practice problem number 2. A 20 kilogram bike accelerates at 10 meters per second squared. What force is being exerted by the person pedaling? Here's our formula. Plug those numbers in. And remember, the units, kilogram times meters per second squared, can be summed up by just saying a Newton. And let's take a look at understanding the net force, because usually there's more than one force acting on an object at any one time. And if those forces are exactly equal, then there's not going to be a change in motion. But if they are not equal and opposite and they don't cancel each other out, then there may in fact be a change in motion. So what is the net force on each of these objects? Remember, force is a vector. Well, the force on the first one is going to be going to this direction, and it's going to be 5 Newton force. So there's going to be a net motion going to the left. The next one, it looks like the force is going to be in this direction, and it's probably going to be exerting a 2 Newton force. You can actually calculate the acceleration that this object's going to move if you knew the mass. And then the last one, there is no net force. And so whatever motion this object is in, whether it's standing still or whether it's moving, doesn't change. It maintains whatever motion it has. If each object has a mass of 10 kilograms, what is the acceleration of each object? Oh, let me go back, sorry. Okay, so in this case, we figured out the force, I'm going to put the force right here, is 5 newtons, okay? And here we figured out the force was 2 newtons. And here we figured out there was no force. So the acceleration for number 3, okay, is equal to 0. Okay, the force formula itself is equal to mass times acceleration. So acceleration is equal to the mass, the force, divided by the mass. So here I'm going to divide it by 10, and I get an acceleration. 5 divided by 10 is, that's 1/2. That's 0.5 meters, meters per second squared. I'm going to write it over here. Meters per second squared is going to be the acceleration for all of the answers. The second one, I've got 2 newtons. Divide that one by 10. Okay, and if you need to use a calculator, by all means, use a calculator to do your mathematical problems. You don't have to do these problems in your head. The answer is 0.2 meters per second squared. All right, Newton's third law of motion is the action-reaction law. For every action, there is an equal and opposite force reaction. The opposing forces are called action-reaction pairs. This will be more important when we get to collisions. But for every action, there is an equal and opposite reaction. Okay, keep in mind that forces are vectors. So it's either a push or a pull. Sometimes there's contact between the objects. Sometimes there's not contact, like with gravity. And because it is a vector, we need to have an arrow that represents the direction that the force is being exerted. And you probably notice I have different size arrows on this slide, and they're pointing in different directions, which tells us that this big arrow, the force is being exerted to the right, or the small arrow at the top, the force is being exerted to the left. The size of the arrow also tells us something. It tells us how big of a force it is. The bigger the arrow, the bigger the force that's being exerted. You're going to see those types of arrows drawn on this thing called the free body diagram, and it really just shows the forces that are acting on any one object, and it can visually tell you if there might be a change in motion in any direction. A change in motion, remember, is an acceleration. Okay, types of forces to consider. Let's go over them one at a time. First off, let's look at weight. Okay, weight is the force of gravity that acts on an object. Okay, and it's basically that, acceleration due to gravity. Apply your mass to that acceleration due to gravity, and you've got weight. So mathematically, we can take our force formula like this, and remember, this is just the acceleration due to gravity there, and we can rewrite it because weight is the force of gravity acting on you or some other object. Remember, that G, 9.8 meters per second squared, is only true, that acceleration due to gravity is only true on Earth. So if you were somewhere else, like you were not on Earth, then you wouldn't have that acceleration due to gravity. And, you might have a different weight. So for instance, if you were on the moon or some other planet, or if you were in outer space and there was no acceleration due to gravity, you would be completely weightless. A lot of times people get weight mixed up with something like mass. So on the next slide, we're going to go over the difference between weight and mass. Incidentally, the acceleration due to gravity is always towards the center of the Earth. So when you're drawing it on a piece of paper, we always draw an arrow straight down to represent the force due to gravity. Okay, let's just pause here and take a look at mass versus weight. Mass is actually the amount of matter an object has, and mass will not change no matter where you are in the universe. Whereas weight, like I said before, is based on the acceleration due to gravity. So if you were on a different planet, or you were just not on a planet, just floating around in space, and there was no gravitational pull acting on you, you would be weightless, although you would still maintain all of the matter that makes you up, and so you would still maintain your mass. Okay? Subtle difference between those two. We often get interchange those words interchangeably because we hardly ever leave the Earth, and so mass is one way that we just, by weighing something is one way that we determine the mass. Okay, the normal force. The normal force is the force that's exerted by the surface on an object. that is in contact with it. So if something is laying on the surface, there is a normal force acting, and it's always acting perpendicular to that surface. So if you had something like a ramp like this, and you had something laying on it, the force of gravity, remember, is straight down. But the normal force would be perpendicular to that surface, okay? Kind of like that. It's not always directly in opposition to gravity. It's actually in opposition to the surface that it's resting on. Tension forces. Tension forces usually apply when something is being held by a rope, string, cable, wire, or chain. And that tension is always directed along whatever it is attached to in the opposite direction of the object. That's a tension force. Here's a good one, friction. A lot of times we'll say neglect the friction because frictional forces are sometimes very, very small. Frictional forces are forces that oppose motion, and they can either oppose motion when things are at rest, and that's called static friction. That opposes just getting something moving to begin with. Once you overcome that static friction and get something in motion, that static friction disappears. And then you've got this thing called kinetic friction, and that opposes motion in movement. So air resistance, water resistance, those are examples of kinetic friction. And if the air is very, very negligent, very thin, sometimes we just ignore it, but not all the time. Okay, this right here is that free body diagram. Again, notice that there are arrows pointing out in all different directions. What we want to do is we want to show the size and the forces acting on any object in a free body diagram. To do that, we need a couple of steps to go through in drawing a free body diagram. Pick one thing to analyze. Don't pick more than one. Draw some kind of a geometric shape to represent that object. A box is nice. Draw arrows to represent each of the forces acting on the object, and make sure the arrows are pointing in the direction that the force is being applied. Also, be aware of how big your arrows are, and make bigger arrows for stronger forces and smaller arrows for weaker forces. Let's take a look and maybe try drawing one. Here's the problem. Book is at rest on the table. Draw the forces acting on the book. First off, you want to draw some kind of a shape representing that object, okay? Everything on Earth has the force of gravity going straight down. This book is resting on the table, so we want to draw a normal force pointing straight up. Now, I drew those arrows pretty much the same size because really they are equal and opposite. Neither of them is actually setting that book in motion. They cancel out. The forces are balanced. Problem number 2. An egg. It's free falling from a nest in a tree. Neglect the air resistance. Well, just pretend it doesn't exist. Draw a free body diagram. So I'm going to draw a box to represent the egg that is falling. And here is the force of gravity pulling on the egg that's falling. It's not resting in the net, so there's no normal force. And it's not going right or left. There's no forces right or left. So that is it. The free body diagram is straight down. And therefore, the egg is actually accelerating straight down. It's getting faster and faster because that's the only force that's acting on it. And there's no counter force not acting on it. Free fall is when the force of gravity is the only force acting on an object. Okay, that's what we call free fall. Okay, problem number 3. Let's look at that book again. This time, a rightward force is applied to a book at rest. So start off with our free body diagram that we had on the other slide. You probably will say there's the force of gravity pulling down. It's resting on the table, so there's a normal force pushing up. You probably realize that there's an applied force pushing it to the side, and there's probably some frictional forces resisting the motion. And you would be right. It would look something like this. Notice that the applied force, this arrow, is a little bit longer than the frictional force. So therefore, there's an acceleration, a change in motion, and it's moving faster to the right than it was before. Now, if it was sitting at rest, it would be moving across the table. If it was in motion, it would then be speeding up across the table. Okay, problem number 4. Skydivers falling with constant velocity. Consider air resistance. Draw a free body diagram for the skydiver. I'm going to draw a couple of free body diagrams here. Let's pretend like here is the skydiver that just steps out of the airplane. When he first steps out of the airplane, the only force acting on him is gravity, pushing downward. And then after he falls for a while, a little bit of air resistance occurs. Now that force of gravity never changes. It's going to stay the same size the whole way. But as he falls a little bit, there's a little bit of air resistance that starts to pick up. So that arrow gets a little bit bigger. Eventually, if he falls long enough, that arrow on top grows until it's the same size as the arrow below him, just like that. And that's when he gets to this thing called terminal velocity, the maximum constant speed obtained when the resistant forces stops the acceleration due to gravity. And so the skydiver here, okay, at the very, very beginning, isn't moving, but he starts to speed up as he falls down. He's getting faster and faster and faster until air resistance catches up. And then whatever speed he's at, he just stays at that speed because now the forces are equal. Now, when his parachute pops open, guess what arrow gets bigger then? This one, because now there's a whole lot of air resistance. And so it slows him down so he doesn't smack into the ground. Okay, there it is. When you get to terminal velocity, the arrows are exactly the same size on the top and the bottom. Before terminal velocity, the air resistance is smaller. After he opens up that parachute, the air resistance is bigger. So a little idea. Now, when he's falling, obviously, when the force of gravity is a bigger arrow on the bottom, it'll be speeding up. The motion will be constantly changing. At this point where they're equal, the motion will not change. Whatever velocity he's at or she's at, stays constant. Okay, problem number 5. A man drags a sled across loose packed snow in a right direction with an acceleration. Aha, with an acceleration. So you're going to have to draw an arrow bigger than the other ones. Okay, remember, there's the force of gravity. There's the normal force. You've got the applied force that should be bigger. And you've got the frictional force, which should be smaller. So you've got 2 different size arrows here on either side that shows the acceleration going to the right. Alrighty, problem number 6. Car runs out of gas and coasts to a stop on flat ground. Draw a free body diagram. Okay, I'm going to draw a free body diagram of the car. I know there's a force of gravity going down. I know there's a normal force going up at about the same size. Now, he runs out of gas. So if the car is moving in this direction and he runs out of gas, is there a force still going in that direction? No, there's no force going in that direction, but there is a frictional force going in this direction. So this one can be kind of confusing because the actual motion of the car is in this direction. It's rolling forward. But because of the friction going in the opposite direction, it's actually slowing down in the opposite direction. So the acceleration is going to be negative. Okay, here it is. When you run out of gas, there's no longer a force on this side over here. Okay, even though it is going in this direction, there is no force in that direction. Remember, the forces aren't telling you which direction the motion is in. It's telling you which direction the acceleration is in. So the acceleration is actually going in this direction, and it's a negative acceleration. Okay, in summary, here we go. All forces are vectors. Newton's first law is the law of inertia. Second law is the force equation. F is equal to ma. The third law is action-reaction. And weight is actually the force of gravity. Okay. Normal force is always perpendicular to the surface, and friction is a force that opposes motion. Thank you for listening. I'll catch up with you later.